Alright, so this is chapter 11, section 9. We're going to work on the three-dimensional coordinate plane, and we're going to use all the things that we have done in the past, the distance formula, the midpoint formula, and the equation of a circle, and apply it to a three-dimensional object. Whenever you get done, you're supposed to do page 705, problems numbers 3, 5, 6, 7, and 10. Alright, so first let's look at what the three-dimensional plane is. What we've been working on so far has been a two-dimensional coordinate plane where you just have x and y. Well, our world is a three-dimensional world, so there is a three-dimensional coordinate plane. And if you notice the picture here, you have your x and y axis, which is your flat surface, and then your z-axis is your height. So you can notice here we have x, the black axis, y is the red one, and z is the purple one. So this is what we mean by a three-dimensional coordinate plane. And just like on the two-dimensional coordinate plane, you can plot points to indicate a position. With the three-dimensional coordinate plane, you can also plot points to indicate a position in the area. So here is the actual coordinate plane. You notice I have my x-axis, my y-axis, and my z-axis. We still do have the origin with the 3 zeros. In our points, if you notice this point here, it says -5, -5, 7. Well, that means it's at -5 on x, -5 on y, and +7 on z. So you notice both of these are over here in the -5 region, and then the z is in the positive region because that's our up and down distance. It's very difficult to plot these points on a two-dimensional plane or on a piece of graph paper because it is a three-dimensional concept. So I will not be asking you to actually plot points, but you do need to understand where the z-axis comes from. Okay, so we've talked about the distance formula, and our distance formula from before was the x minus x squared, y minus y squared. Well, the distance formula in a three-dimensional plane just adds the z coordinates on the end. So if I have these 2 points on the three-dimensional coordinate plane, to actually figure out what the distance between those points are, I just go ahead and put it into the distance formula just like I would if it were just a two-dimension. I just add the z as the third dimension. So if you notice right here, I've put in my 4 minus -5, which makes it 4 plus 5. Then I do the y, 0 minus 2. And then I do the z, -3 minus 1. I do all the calculations that I need to do. And remember, if you are trying to square a negative number, you need to put that negative number in parentheses before you square it. Otherwise, the calculator will square the number and then put the negative sign on last. So whenever I go through the process, I get the square root of 101, which is about 10 500. So the distance between these 2 points in a three-dimensional coordinate plane, so in other words, if I have these 2 points in a box, the distance between the 2 points is 10 500. A sphere is a three-dimensional object, so if we're going to do the equation of a sphere, we're just going to need to add that third dimension. And just like with the distance formula, we added the third one, the z. Well, now the center of our sphere is going to be three-dimensional. It's got an x-coordinate, a y-coordinate, and a z-coordinate. It is the exact same formula that we use for a circle, except it has the third dimension. So what I would just do is, okay, so I've got the center of the sphere right here at 3, 0, and -1. I've got the radius of 8. So I just put it into my equation. The 3 goes in for h, the 0 went in for k, and since it was y plus 0, I didn't have to record it, and the -1 goes in for j. So that makes it z plus 1. Here I had squared my radius, so radius squared, 8/8 or 64. This is the equation of a sphere, not very much different at all from the equation of a circle, except we add the third dimension to it. Midpoint formula, exactly the same again, except I've got x, I've got y, and I've got z. So I just plug it all in. X, negative 5 plus 4 divided by 2. Y, 0 plus 2 divided by 2. And z, negative 1, or 1 plus negative 3 divided by 2. So that was the three-dimensional midpoint formula. There is something called the box diagonal formula that is based on the three-dimensional coordinate plane distance formula, except instead of having to do the subtraction, you just do length squared plus width squared plus height squared. And again, since we're talking in 3 dimensions, a box has 3 dimensions. And then this is asking you, well, what's the longest pole that I can put into the box? I'm just going to substitute all of these into this formula, and I can put a 141 centimeter pole into the box. And this is just an application of the distance formula. When you do the box, you're putting it in a convenient location. So the origin is going to be one of the corners of the box. So since the origin is one of the corners of the box, then we have the length, width, and height to use it to fit into the box. Okay, so that's all for this section. Remember that now what you need to do is you need to go to page 705, try problems 3, 5, 6, 7, and 10. Thank you.